Hey everyone, going to give a really quick explanation of asymmetric encryption and the RSA algorithm. So if you're not familiar with the concept of asymmetric encryption, it's a really cool idea. It's the idea where if you have a public key and a private key, and if anyone wants to speak to you, you give them your public key. In fact, you give anyone in the world who wants to talk with you your public key. And they encrypt their message using the public key, and then they send it to you, and you decrypt it using the private key. And only the public key can encrypt, and only the private key can decrypt. It's really cool, and the analogy for that is like a padlock. And you go around to anyone in the world who wants to talk to you, and you give them an open padlock. And if they want to write you a message, they write a message, put it in a box, and then they lock the padlock, and they give it to you. And notice how even though they encrypted the message, even if they wanted to decrypt their own message, they couldn't, because they don't have what you would have, which is the private key. Or in this example, it's a literal physical key, because you require the physical key to unlock the padlock. So this is a really neat illustration. You'd give everyone in the world one of these padlocks, and in RSA, the equivalent of that is called the public key. And only you would keep this key, which in RSA we call the private key. So it's this really cool system where you can communicate using asymmetric keys. So what should I do? Let me show you a little bit more detail what the public and private key actually look like. So what does a public key look like? Well, they're actually two sets of numbers. Public key, well, that looks like this. It's two numbers. It's E for encrypt and N. And that might be, let's just use an example, E might be 7 and N might be 33. Now you can't really just make these numbers up. There's an algorithm to derive them, and I'll show you that in a second. But the private key, well, that's key. That is made up of D and the same N from above. And an example of that might be 3 and 33. Notice how the N is the same for both of them. So if you want to understand RSA, it's really important to know how to use these numbers. So to encrypt a message, let's say you have the message, I love you. Normally what you do is you treat this entire message as one number. So you might give each of the letters a particular number and treat the whole thing as one massive number. But just to simplify things, we're going to say maybe the letter U. And maybe the letter U has the number 2 associated with it. Cool. So we take that, and the formula for RSA for encrypting stuff is this. So you take the ciphertext, which is known as C, you take the plaintext, and you raise it to the encryption key, that value there. And then you just mod it by N. And then when it comes to decrypt, well, it's quite simple. It's like almost the reverse process. You want the plaintext, you take the ciphertext, raise it to the power of the decryption key, D for decryption, and then you mod it by N. Decryption key is also the private key, right? And only you, the owner of this key, has the private key. So let me do some worked examples. Let's say I have 2, that's my plaintext. Let me encrypt it. So the plaintext is 2. I want to raise it to the power of E, which I know from this example is 7. Mod it by 33. It's pretty easy. I can do this in my head. That's 128 mod 33. Now what mod means is that just means divide 128 by 33 and then figure out what the remainder is. So if you're not too familiar, you can just go to Google and type this in here. Here I have an example from before. You can just do 128 mod 33. But if you don't have that on your calculator in an exam or something, it's quite easy to do. What you do is you just do 128 divided by 33. You'd see how many times it wholly fits in. So you can see here it's just 3. So 128 fits in 3 times wholly. So I just modify this and I say 128 minus, in brackets, 3 times 33. And this will give me the remainder here, 29. So that's the same answer we had before. So this answer down here is 29. So that's the ciphertext. That's the value that is encrypted using RSA. To decrypt it, I just move it over here and we look at C. So what was C? C was 29. We just figured that out. Let's raise it to the power of D. What's D? Well, D is 3, so let's raise it to the power of 3. And again, we just do the same thing. We mod it by 33. So it's really elegant. On this side, you raise the power of the encryption key, and to decrypt it, and mod it, I should say, mod it by n. And then to decrypt it, you raise it to the power of the private key, and then mod it by n. Really elegant. So let's calculate this one. What is it? 29 to the power of 3. Let's figure out what that is. That fun number there. Oop, copy. And that number again, mod 33. And surprise, surprise, the answer is 2, which was our original plain text here, which is you. So that's what the answer is you. So that's really cool. That's the example of using RSA for encryption. There's another really cool feature of RSA, which is called digital signatures. And the idea is if everyone has my public key, and they know that that's my public key, can I do something with the private key, which they can then use the public key that they have to verify that it came from me? And if they can use the public key to verify that something was signed with the private key, then they know it must be me because only I have my private key. So what they do is they actually flip the maths a bit here. And let me move my head out of the way. So this is what we've seen above for encryption, but to sign something, instead of using the encryption key, which comes in the public key, to sign something, let's call it the signature. You take, maybe you have like a certificate, a will, and you know, what you'll do is you'll take a hash of it. And normally what they'll do is they'll sign the hash. So let's say we've done that, and we have the message which we want to sign. So to sign it, you just have to sign it with a public key. You do exactly the same process, but instead of using E up here to encrypt it, you just raise it to the power of D, and you mod it by N. So that's that there. And they get the signed document. What you'll do is, you have the document. You have the document. You'll hash it, and you'll take the hash and you'll sign it and you'll send it across. The other person will get the document. They'll hash it themselves and they'll figure out what the hash is. And then to verify, what they'll do is they'll take the signature. They'll raise it to your public key. Now your public key is E. Stands for encryption because it's normally used for encryption. They'll raise it to E, and they'll mod it by N again. And what they should get is they should get the original message that was used in the original signature. Now, if this message matches the hash of the document, then they know, whoop-de-doo, this is actually the legitimate original document that was originally signed. So that's a really cool application of RSA. It's digital signatures. It's used absolutely everywhere, including in your browser, to make sure that you're communicating with the right person. Because every certificate in your browser is signed using this process exactly here. So I mentioned before that these are the public and private keys, but we don't just make these numbers up. There is actually an algorithm to figure them out. So these steps we went through here are all very important, very critical to know. And I'm going to go through the more detail here about how to calculate those numbers. It can be quite scary, but bear with me. We'll survive. I believe in you. You can do it. I always recommend following along with a little tutorial. So there's one I will recommend, which is this one here. And you can find it by Googling RSA Crypto Worked Example, and the CS Virginia website will come up. It's a really good one. And they step through all the maths here, which is really good. Follow along. Wikipedia is fine as well. But let's step through the problem. And the first way to figure out your public key, which is your E and your N, and your private, which is your D and your N, is you start by picking two numbers. So the two numbers are called P and Q. Now you really have to mind your P's and Q's because these should be prime numbers. Now typically they should be really large prime numbers, but because I don't hate myself, I'm just going to pick really small numbers now. So one prime number, well, I'll pick 3 and I might pick 11. So they're both prime numbers. And what I do is I figure out one of my first numbers, and we just figure that out by multiplying P times Q. So I can do that quite easily. 3 times 11 equals 33. Excellent. I've done my first part of RSA. Figured out my first number. The next thing I need is a really fun one. It's called Euler's twoshot, which is this lovely thing here. It's great fun. It can be quite scary, but it's really simple. Euler's twoshot, you just take P that you calculated before, subtract 1, and then Q that you picked before up here, subtract 1 as well, and multiply them together. So let's do that really quickly. 3 minus 1 and 11 minus 1 equals, well, that's 2 times 10. Euler's twoshot is 20. That's a number that we use intermediately to figure out some other values. So we remember that Euler's twoshot equals 20. All right, now we've got n, which is equals 33. We've got Euler's twoshot. Now what we do is we have to just randomly pick our encryption value. We just randomly pick a number e. So pick e. Now there are a few restrictions on e. It needs to be between 1 and Euler's twoshot. So basically, it needs to be e needs to be between 1 and 20, and it can't have any shared factors of 20, if that makes sense. So, but for a number between 1 and 20, well, all the options are it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. What a relatively coprime means is that E can't have any shared factors of 20. So what are the factors of 20? Well, 20, you can get 20 by multiplying 1 and 20. You can get it by multiplying 1 and 10. You can get it by multiplying 4 and, 4 and 5. So they're the factors of 20. So that means we can't choose those. So we can't choose 20, can't choose 1, can't choose 2, can't choose 10, can't choose 4, can't choose 5. So let's pick the value 7. So what I'm going to do, we're running out of space, aren't we? Let's raise this factors here. We'll say let e equal 7. Now what we need to do is that's awesome. We've got everything we need for our public key, right? We've got e, which is 7. We just decided that, and n, which is 33 over here. Cool. So we've got our public key. Now we need to figure out our private key. So our private key, that's D. To find D, we need to solve this question here, which is D times E. When divided by 33, the remainder should be 1. So the way we write that is 1 mod, why did I say 33? Silly me. It's actually not that. It should be, I'll just write this math here so you can see the formula. So let me say that again. We need to solve this puzzle here, this mathematical expression, which says what number, aka D, when times by E, has a remainder 1 when it's divided by Euler's twoshot. Very complicated. I'll just fill it out. So we're saying D times E, which we have, 7, has remainder remainder 1 when divided by Euler's totient, which remember we said up here, Euler's totient is 20 divided by 20. So I hope that makes sense. Let me just show, let's, for example, look at the case of 1. So 1 times 7, well, that's 7. And I'll just do this half of it. 7 divided by 20 is 0 with remainder 7. So that doesn't equal 1. So 1's not an option. Get rid of all these blip. So let me try 2. So 2 times 7 equals 14. 14 divided by 20 equals 0 with remainder of 14. So the remainder here doesn't equal 1, so that's not a solution either. Oh, the joys, the joys. This is why I love maths. So let's try 3. Let d equal 3. If d equals 3, then that becomes 3 times 7, which equals 21. Now 21 divided by 20, or this totient, equals 1 with a remainder of 1. And that's that remainder there that we're looking for here. So whenever we find a solution which has remainder 1, perfect, we've found the correct version of D, a suitable number D. So there we go, we have all the values we need now. So we have our public key. That's made up of the E for encryption key and the N, also known in this example as E, which we just picked, which was 7 and 33. Private key is it's D and N, which is, I just calculated it, I should remember that, D and 33. So there you go. It can be quite daunting. You've got all these numbers and Greek letters and look at all this maths on the page. But it's quite simple. Pick 2 prime numbers, multiply them together, and you've got N. Then subtract 1 from each of those the P's and Q values, multiply them together. That gives you this intermediary value called Euler's totient. Pick a random E that's less than Euler's totient and greater than 1. And just remember it has that side condition that E can't have any of the same factors as this 20 value here, Euler's totient. And then just solve this formula here. D times E, so the public and the private key, the encryption and the decryption key. When they're multiplied together, when you divide that number by Euler's totient, that intermediate value over here, should only have a remainder of 1. And that's essentially RSA algorithm. If it doesn't make sense, and it's important to know this, how to calculate it, I definitely recommend reading a worked example such as this and getting your head wrapped around it. There are some shortcuts to solve this problem here, but we won't go into them for this video. So I hope that makes sense and it's a little clearer. And good luck with your RSA questions.